In this unit, we've been talking about matter and change. And in this segment, I want to talk a little bit about two kinds of matter that are super important to you and me as humans, and that is air and water. Some of this is a review. We've already talked about some of this stuff, but a lot of it's brand new. Recall that a molecule is another fundamental building block of matter, and a molecule forms when two or more atoms are chemically bonded together with covalent bonds. And recall that a covalent bond can form between the same type of atoms or different types of atoms. And so H2O2, N2, those are all molecules. They're also elements, right? However, these are all molecules, but they're compounds, right? So these are compounds, these are elements, they're all molecules. So we can represent these molecules like this. Each one of these bars represents one covalent bond. And so each bar is two shared electrons. And so when hydrogen gets together, right, each hydrogen atom has one electron. And they each share the electron that they have. And so in a hydrogen molecule, then there are two shared electrons. In an oxygen molecule, there's four shared electrons. That's what's represented here. Two covalent bonds, two electrons for each covalent bond. We have a total of four shared electrons. Nitrogen actually has six shared electrons. We'd call this a single bond, this is a double bond, and this is a triple bond. More complicated molecules exist too. This guy's water, this guy's carbon dioxide, this guy's alcohol right here. And so notice, oxygen, carbon, hydrogen, we can make all different kinds of things with oxygen, carbon, and hydrogen. Again, these are elemental molecules, and these are molecular compounds. Here's another visualization of the hydrogen, nitrogen, oxygen, and chlorine molecules. These are all called diatomic molecules, recall. So diatomic molecules are formed up of two atoms of the same type. So again, this stick represents a covalent bond, which is when two atoms share electrons. In some of these molecules, there's complete symmetry. For example, in the hydrogen molecule, each hydrogen atom is pulling just as hard on the electrons, and so these two electrons here are shared equally. Same thing with oxygen. These four electrons are shared equally. Same thing with nitrogen. These six electrons are shared equally between the two atoms. However, if we start talking about molecular compounds, where we've got different types of atoms that are bonding, then each type of atom might be pulling a little bit differently on those electrons. So, for example, in water, we find that the oxygen actually pulls harder on the electrons than the hydrogen. So they are sharing electrons, but it's not an equal split. It's called a polar covalent bond. And so an example of a non-polar covalent bond, like I just said, would be a hydrogen molecule. In that case, the two hydrogen atoms are sharing two electrons, and they're sharing them equally. And so we call this non-polar. However, in lots of compounds, for example, in hydrogen chloride, which is a compound, a molecular compound, these electrons are shared unequally. In the case of hydrogen chloride, the hydrogen atom really doesn't have much of a pull on that electron, whereas the chlorine has a very strong pull. And so what we end up finding is that the chlorine has a slight negative charge, and the hydrogen has a slight positive charge. It's not equal to an entire electron, right? So this is not an ionic bond, right? The chlorine isn't stealing the electron, but it's an unequal sharing. An unequal sharing of electrons is still a covalent bond, but it is a polar covalent bond. We'll come back to that in just a minute in the context of water. It has some important consequences in the water molecule. Okay, let's talk really quick about the composition of air. I've hinted at this a little bit, but I've never quite just laid it all out there. Most of the air that you and I breathe is nitrogen. So almost 80% of the air that you and I breathe is nitrogen, and we don't interact with it at all. We breathe it in, we breathe it right back out. That's all. Oxygen, which we do use, you and I run on oxygen, makes up the next biggest portion, about 21% oxygen, and then everything else kind of falls into this other category. So, what type of matter is air? Is it an element, is it a compound, or is it a mixture? Well, we've seen this before. Hopefully you remember that it is a mixture. It's a mixture of nitrogen, oxygen, and some other stuff. What other stuff? Well, almost all of it, 99.997%, is nitrogen, oxygen, argon, carbon dioxide. Argon's a surprising one. I think most people would not have picked that. Again, we don't interact with it at all. We breathe in the argon, we breathe out the argon. Same with the nitrogen. Now the oxygen, we do use, right? And carbon dioxide, notice what a tiny fraction it is when I breathe it in. It's much greater than that when I breathe it out. But be careful, it's not almost all carbon dioxide. It's still mostly nitrogen, still mostly oxygen and nitrogen, but there's more carbon dioxide that I exhale than what I breathe in. All right, what else? A little bit of neon, tiny bit of hydrogen, helium, methane, krypton, sweet. Carbon monoxide, xenon, ozone, etc., etc. Sulfur dioxide. It turns out sulfur dioxide is what tarnishes your silver plates. I know you've all got a cabinet full of silver plates. And it's sulfur dioxide, actually, that reacts with the silver, creating a new substance, a new compound, silver sulfide. And silver sulfide is the tarnish, that black stuff on your silverware, your actual silver stuff. Okay, so that is what is in dry air. I haven't included water because it can vary a whole lot. The amount of water in air can vary a whole lot depending on what the humidity is, where we live, what time of year it is, things like that. Okay, so let's talk a little bit about water, another very important substance for you and I. This drawing right here just shows all of the electrons in the outer energy level of the oxygen plus the electrons from hydrogen. We haven't necessarily talked about the energy levels of the atoms, so we'll just say that these are the electrons available for interacting with other atoms. And of course, these two right here, they form a pair with the hydrogen. And so we form one covalent bond here. These two electrons here form a pair with this hydrogen atom here, and they form a covalent bond there. An interesting thing happens to water. And the first thing that's interesting is that it forms this bent shape. These electrons here, these unshared electrons, they end up kind of on the far side of the oxygen atom. And so we end up with this bent shape. It's 104.5 degrees between the bonds, between these two bonds here. And so water ends up taking on this bent shape. In addition, the electrons are not shared equally between the oxygen atom and the hydrogen atom. And so since they are not shared equally, what does that say about those covalent bonds? Are they nonpolar, polar, ionic, or are they a hydrogen bond? Well, hopefully, if you've been paying attention, then you know that this is a polar covalent bond. So indeed, these covalent bonds in water right here, they are polar, which means that there's a slight charge to the hydrogen atoms and a slight charge to the oxygen atom in the water molecule. We end up with a partial positive charge on the hydrogens and a partial negative charge on the oxygen. Now, I've added this 2 here. Chemistry class would not show that. The delta just means it's a partial charge. It means it's not a complete charge of an electron, right? Elsewhere in our electricity unit, we learned that charge really only shows up in packages of electrons and protons. But here, since we're talking about shared electrons and unequal sharing, we actually end up with a charge that's less than an electron, right? Because we're talking about 2 electrons that are just unequally shared. And so, but the point is that the hydrogens get a little bit positive, the oxygen gets a little bit negative, but the total charge on the water molecule is 0. So partial negative on the oxygen, partial positive on the hydrogen, but overall the water is neutral. And we investigated that elsewhere in the semester. Okay, so the combination of this bent shape and the polar nature of the covalent bonds makes for something very interesting with water. It means that we have a slightly negative oxygen atom here and a slightly positive hydrogen atom here in another molecule. Well, we've learned about positives and negatives, right? Positives and negatives are attracted to each other. And so the positive in the hydrogen atom of one molecule is going to be attracted to the negative in the oxygen atom of another molecule, and it'll cause them to kind of stick together. We call this a hydrogen bond. Now be careful. A lot of people see this word hydrogen and they think, oh, it's a bond between hydrogen atoms. It's not. A hydrogen bond is a bond between an oxygen atom in one molecule and a hydrogen atom in a neighboring molecule. Now, it can happen in other molecules too. And so it's a bond, technically, a hydrogen bond is a bond between a hydrogen atom in one molecule and an oxygen, nitrogen, or a fluorine atom in a neighboring molecule. Now, we're not going to talk about hydrogen bonds in any other compounds except for water. So this hydrogen bond creates an electric attraction between, again, the hydrogen in one atom and the oxygen in another atom. So hydrogen bonds are between neighboring molecules, whereas covalent bonds are within a molecule. And the covalent bonds are much stronger than these hydrogen bonds. So for example, we had a question earlier in the semester, what's in the bubbles of boiling water? And the correct answer, right, was water vapor. So there's enough energy on our stove to break the hydrogen bonds apart, but we still have water. So there's not enough energy on our stovetop to break the water molecules into oxygen and hydrogen, but there is enough energy to break the hydrogen bonds between water molecules in the liquid, creating a gas. In fact, a hydrogen bond is only about 1/15 as strong as a covalent bond. Here's a question for you. When do you think hydrogen bonds exist? In the solid state, the liquid state, the gas state, or perhaps more than one of those? Okay, well, remember that in a gas, the molecules aren't actually touching each other, right? They're just bouncing off of each other. Whereas in a liquid, they are next door neighbors, but they can kind of move around, right? And in a solid, they're next door neighbors, but they're not going anywhere. So we can get hydrogen bonds in either liquids or solids, but not in the gas state. And so that's why a minute ago when I was talking about how on your stovetop, you're actually breaking those hydrogen bonds in order to create water vapor out of liquid water. But again, we're not breaking the hydrogen and the oxygen apart. That requires 15 times more energy. Generally speaking, more energy than you're going to get off of your stovetop. If we were to kind of zoom in, then we'd see here, in ice, we've kind of investigated this a little bit, right? This bent nature and these hydrogen bonds, this is part of why ice expands when it freezes. And we've talked quite a bit about that. In water, in liquid water, we still have the hydrogen bonds. But they're more random, right? And they're constantly being broken and formed with another molecule, broken here, formed with another molecule there. Whereas in ice, right, they've got the same, every molecule has its same neighbors throughout time. If we were to imagine a 3D visualization of an ice crystal, this is what it looks like. And so it creates this real regular pattern. And again, we talked about this. What's in the middle here? Nothing, right? Completely empty space. And so this is why ice expands when it freezes. And it's also why this bent shape, right, and the polar nature of the covalent bonds in water, it's why we get such interesting shapes for snowflakes. So they say that no two snowflakes is alike, and maybe that's true, but it's certainly approximately true. And so it's interesting, you get this high degree of symmetry. Why? Because the conditions where the snowflake form, right? The snowflake's so small that the conditions are not different on one side of the snowflake than they are on the other, right? And so whatever it's doing over here on this little arm of the snowflake, the same thing is happening over here. And so it grows and grows and grows. But there's another snowflake right over here. And you know what? Going over there far enough, the conditions are not exactly the same. And so we get a slightly different shape for the snowflake. Pretty cool, no matter how you slice it. There's a lot of different shapes that can form, and it really depends on the temperature. And this over here, supersaturation, it's basically the humidity. right? It's like how saturated is the air with water. And so these two things determine what shapes you get. And you don't need to memorize this chart or anything like that. I mostly just think it's interesting. Depending on the temperature and how humid the air is, we might get plates, or we might get these hollow columns. Those are interesting. These classic snowflake shapes are called dendrites. Or we also get these plates, which are interesting, and also, some of these thin plates are sort of classic snowflake shape. But these are the real beautiful ones that you see pictures of. Other interesting phenomena related to water is that, let's think about its boiling point. Most of us know what the boiling temperature of water is. This question is a big if. Let's look at this table here. We see CO2, it's got a molecular weight of 44, its boiling point is 78.5. O2 has a molecular weight of 32, and a boiling temperature that's quite a bit colder, right? And N2 has a slightly higher, a slightly lower molecular weight and a lower boiling point. So here's the molecular weight going to 18. What do we expect to be here? Again, if you know what the boiling temperature of water is, that's fine. That's not what I'm asking here. I'm asking you to do some pattern recognition. If this trend continued, what would we expect to be in this slot right here? Well, we see that as the molecular weight decreases, the boiling point also decreases. So, if we're just going with this pattern, I expect something that's lower than 195.8 Celsius. But that's not the case, is it? We know that water's boiling point is actually 100. It's actually way higher. Why is it? Why doesn't it fit this pattern? And again, it's those hydrogen bonds, right? Because there's something sticking these molecules together, and it's those hydrogen bonds. The hydrogen bonds are holding the molecules together, and so it takes extra energy to make it boil. It takes a higher boiling temperature, right? So it takes a higher temperature to actually break those bonds apart and liberate the molecules into their gas form. Another interesting feature requires just a little bit of background here. So recall that when we measure the temperature of something, you're actually measuring how much the atoms or molecules are moving, right? We touched on this briefly earlier in the semester. So if I say, it's 60 degrees in this room, it's a little warmer than that, 68 degrees in this room. Well, really what I'm telling you is how fast the molecules in this room are moving. And if we increase the temperature, we would make the molecules move even faster. Some substances require more energy to change the temperature than other substances, right? So, there's this classic thing of, back in the old days, people used to take a hot water bottle to bed with them. They'd fill up a bottle with some boiling water, they'd take it to bed with them, and to help them keep them warm all night. You know what? Not all substances would give off as much energy as they cooled down as that water. Water is a very good choice for that. In fact, if you were to use something like a piece of aluminum instead, then it wouldn't keep you nearly as warm, even if it started at the same temperature as the water. Well, why is that? Because water releases a different amount of energy when it cools down than aluminum does. In fact, water releases something like 5 times more energy for every change in 1 degree Celsius as an equal mass chunk of aluminum would. It's kind of crazy to think about. The number that describes this is the specific heat capacity. The specific heat capacity is how much energy it takes to increase the temperature of 1 gram of a substance by 1 degree Celsius. So naively, you might think, it just takes the same amount of energy, right? If I put a piece of aluminum on my stove and I keep an equal size, equal mass, I should say, piece of, say, iron on my stove, and I just turn them on to medium, then, 10 minutes later, they should be the same temperature. It's not true. It takes different amounts of energy to change the temperature of different kinds of things. And it turns out that water has a very, very high specific heat capacity. If you look at this, these are common substances, right? Water has a heat capacity that's basically 40 times greater than gold. Right? And so what does that mean? It means if I've got a kilogram of gold and a kilogram of water, it takes 40 times more energy to change the water by, say, 10 degrees than it takes to change the temperature of the gold. It's kind of crazy. And so this has some really interesting consequences. Water helps to moderate the climate. And so, if you look at a place like Seattle, which is farther north than we are, then they have much warmer winters than we do. Why? Because they're right next to the water, and the water doesn't change temperature very quickly. If you look here at, sand, concrete, some rock-like substances, they have heat capacities that are much, much smaller than the heat capacity of water. What does that mean? It means that they change temperature much faster. So maybe you've heard this about deserts, right? Deserts have very high daytime temperatures, but they also have very low nighttime temperatures. Great temperature swings. Why? There's no water around to regulate the temperature. So if you live next to a large body of water, it's going to tend to moderate the temperature. It's not going to get as hot in the summer, and it's not going to get as cold in the winter. And overall, water helps to regulate the temperature on Earth. On the moon, where there is no water, right, the exact same distance from the sun, daytime temperatures are like 200 degrees Fahrenheit, and nighttime temperatures are like negative 300. So, ridiculous temperature swings with no atmosphere, and especially no water to regulate the temperature. That bent shape with the polar nature of the bonds, that also gives water this really high surface tension. If you've ever seen a little water skipper in a pond, right, they're relying on the surface tension of the water to not really float, but rather to not go into the water. It's really the tension, the surface tension of the water that's holding the water skipper up. And if you're careful about it, you can float a paper clip in some water. You can float even a small coin in some water if you're very careful about it. Now, this paper clip is not truly floating in the sense of what we talked about when we talked about buoyancy and density, right? It's not floating in that sense, because if I just stir this water a little bit, then the paperclip will sink. And so it's really this force holding the paperclip up. Where does that force come from? It comes from the hydrogen bonds. The molecules of water, they don't want to separate and let that paperclip through. They stick to each other. It's those hydrogen bonds. Again, it's that bent shape and the non-polar nature of the covalent bonds in water that makes this happen.